Hello! In previous videos, we have learned that the expectation of the sample mean is equal to the expectation of the random variable. This result has proved rather useful, so in this video we are going to ask if there is a similarly useful expression for the variance of a sample mean. Let's thus work out what the variance of a sample mean is equal to. We first note that what we are calculating is shown here. Notice that the two sums in this expression are sample means, which are calculated in the usual way. Now the second expectation here is straightforward. As discussed on the previous slide, the expectation of the sample mean is equal to the expectation of the underlying random variable. We will thus call this quantity mu in what follows, and thus rewrite the expression here as shown here. Let's now turn to the sum that appears within the square. Let's forget about the expectation first of all, and just consider the square of the sum. We can rewrite this square as follows by writing out the square and the sums explicitly, and by doing the easy bit of the calculation, the squaring of 1 over n. We now need to multiply out these two brackets. To keep myself on the straight and narrow here, I prefer to use the method that I was first taught at age 14 when I first learned to multiply out brackets. In this method, you make a table like the one shown here. You write the terms in the first bracket as the headers for each of the rows here. Each column is then headed by one of the terms in the second bracket. Once you write out this table, it is easy to determine the various terms that appear in the expanded expression. You simply fill out each element of the table by multiplying the term at the top of the column by the term at the left-hand edge of the row. In addition, the geometry here allows you to make some simple observations about how many terms there should be in the table and hence the final expanded sum. If there are n terms in the first bracket and m terms in the second bracket, then the total number of terms in this table will be n multiplied by m. In this case, where the number of terms in both the first and second bracket are both n, the number of terms in the table is n squared. Having expanded the brackets and put all the resulting terms in this table, we will now apply the expectation operator. If we look at this element here, we are calculating the second moment of the distribution for the random variable capital X. We know, however, that the variance of x, sigma squared, is equal to the second moment of x minus the expectation, mu squared. We can thus write the second moment of the random variable capital X as mu squared plus sigma squared by rearranging the definition of the variance. Now recall that we are calculating a sample mean, and that x1, x2, and x3, and so on, are all identically distributed random variables. The consequence of this is that the expectations of all of the terms on the diagonal of this table are equal. There are n terms on this diagonal in total, and we can thus write the sum of all these diagonal terms as n upon sigma squared plus mu squared. Now consider this term here. The random variables are all independent, and thus the expectation of x1 times x2 is equal to the product of these two expectations. In addition, x1 and x2 are identical random variables as they both appear within a sample mean, and their expectations are thus identical and both equal to mu. This term is thus equal to mu squared. Now notice that every term that is not on the diagonal is the same as this one. There are n squared elements in the table in total, n of them are on the diagonal, and thus n squared minus n must be off diagonal. The contribution of all the off diagonals to the final quantity is thus n squared minus n, all multiplied by mu squared. We can insert everything we have learned into our expression for the variance as shown here. Multiplying out the brackets gives the following, and if we then multiply out all the terms in the brackets that remains by 1 over n squared, we get this. We can cancel out the plus and minus mu squared in this expression, and also the plus and minus mu squared over n as shown here. We thus arrive at the following final result. The variance of the sample mean is equal to the variance of the underlying random variable divided by n, the number of random variables that the sample mean was computed from. To summarize then, if we calculate a sample mean by adding together a series of identical and independent random variables, xi, with expectation mu and variance sigma squared, the resulting quantity, the sample mean, is a random variable. The expectation for this random variable is mu, and the variance is sigma squared over mu. The fact that the variance of the sample mean decreases as we increase the number of variables that are used in its calculation explains that why sample means that are calculated using more random variables are more precise estimators for the true expectation than sample means that are calculated from fewer random variables. This result is hugely important, so take some time to make sure you understand it and its significance. Thank you for your attention.